All right, hello everybody. We're going to go ahead and get started today. We're going to be finishing up soils, be talking about those physical and chemical properties. Here's a quick chart that kind of breaks down all the different properties of soils that you are responsible for knowing. Highly recommend that you print this out. If not, then write it out. Obviously, that's going to take a lot longer, but this is going to be super useful for studying when we get to the unit test. All right, so we're going to start with physical properties for soils. And physical property is largely going to be defined by the size of the grains that make up your soil. So all soil is not made up of the same grain size, even though it kind of feels that way when you hold it. But there's a couple of distinct sizes that exist. The largest soil grain size, which is anything less than 2 millimeters, is considered sand. So think about sand that you have at the beach in your hand. You can feel the individual grains when you run it through your fingers. It's relatively large. Next, you have silt. Silt is a little bit smaller than sand. I think it's about 0.5 millimeters to 0.005 millimeters. It's definitely more smooth. You can feel grittiness a little bit. It's kind of like a fine sandpaper. But overall, it is smaller than sand, and seeing individual grains with silt is very difficult to do unless you have like a microscope or something. And then you have the smallest grain size, which is clay. And clay is incredibly small particles of soil, not visible at all with the naked eye. You need a very powerful microscope in order to be able to see it. In fact, if you think about using clay like you have in art classes before, it's very smooth, and that's because the particles are so small, it feels that way. Okay? Now, how much sand, silt, or clay you have is going to kind of determine a lot of properties about your soil. So, for example, let's say I have a soil sample, we'll call it soil sample A, and it is made up of 20% sand, 10% silt, and 70% clay. So this soil sample is made up of a different percentage of each of those grains that we talked about in the previous slide. Well, this percentage of each type of grain is going to be known as the soil texture. And the soil texture is identified by these percentages. Now, each type of soil, based on its percentages, is going to have a distinct name. And in order to find what the name of our soil is, we're going to use this soil texture triangle here to the right. This is a tool that you are responsible for knowing how to use because it may appear on future exams. So it looks a little complex, but let me go ahead and go over this example, and maybe it'll make it a little easier. So essentially what you need to do is take your percents and find where they are on each given axis. So I have my percent clay here, percent sand down here, and my percent silt there. So let's start with clay first. So I have clay is 70%. So I'm going to go up the clay side until I get to 70% right here. Okay. Next, I have silt that is 10%. So I'm going to go here to silt, and then I'll go down to 10. So 10% following this line, 70% to here. So we can see that the 70 and the 10 meet here. And if I follow this line down, it should lead to 20% sand. So I go down, and yep, there's 20% sand. So essentially what you're doing is just finding where the three lines meet. So they meet right here. So this soil would be just called clay because it's predominantly clay. But you can have other types like sand and silt as well. And then you're going to see this word a lot called loam. And loam is just a mixture of all three. So like if I had this right here, this would be 30% clay, 40% sand, and 30% silt. So loams mostly just mean that it's an even mixture of all different types of soil textures, and that's going to be important for fertility later. Now, within your soil texture, it's going to affect a few things. The first one being porosity. And porosity is essentially how large are the air gaps that exist between your different grains. So here I have a couple of sand grains that are attached together, and you'll notice that between the sand grains there is a large air pocket. Compare that to something like silt here, and you can see that the air pockets are much smaller. So the amount of air available between the grains, we refer to this as the porosity. And the porosity is going to affect a couple different factors about the soil itself. First, if you have high porosity, it's going to increase your permeability. Permeability means just the ability of water to flow through. So water should flow through sand faster than it does clay. So we see clay over here. We can see low porosity, low permeability. However, the higher your porosity or permeability, the lower your water holding capacity is going to be. And I got that spelled out up here if you need to see it. So if you have more air between the grains of soil, your water holding capacity will go down because less water is able to be held by that soil because it just simply goes right through it. Okay. Clay, on the other hand, since it has very little area for the water to pass through, it's much better at holding water. So we say it's a high water holding capacity. Now, how do we test for soil texture? Well, we use something called a water jar sample. So essentially what we do, and you'll be doing this in class next week, so I'm just going to kind of quickly run through it. We take a sample of soil, like we see here. We put water into it, and then we shake the soil sample up until all of the soil is suspended in the water. We then let it sit and give it 24 hours to settle. Now, since sand is the biggest grain, it's going to fall first, and then silt, and then finally clay will fall last. Okay? And then we can determine what percentage is sand, what percentage is silt, and what percentage is clay by measuring them with a ruler, and then just doing some simple percent math that we've done already in class. Next, if we want to determine the water holding capacity, we can use a setup like this, in which we take the soil mixture and we put it into a jar that has an area at the bottom and water can escape. And then we just put a fixed amount of water into it. Depending on how much comes out the other side, well, the other amount must be held by the soil itself. So that gives us our water holding capacity. Both of these you will run in class and you'll get a better idea of them once we do. Now, that is it for physical properties. Let's go ahead and move on to chemical properties. So chemical properties is essentially just A, what are the elemental makeups of your soil, and B, what is the pH of your soil? Is mostly what we're going to focus on in this class. Now, all life is going to require these 5 nutrients: carbon, hydrogen, oxygen, nitrogen, and phosphorus. And as we talked about in the first unit, the amount of nitrogen and phosphorus is often in low concentration. So that's going to be important when we talk about chemical properties. So chemical properties, as I said before, are just the concentration of these chemicals. Often we'll use fertilizers to kind of help adjust those chemical properties, but this is going to be important when we talk about fertility of soil and the ability of soil to grow. Now, the other one is going to be pH, and pH is the amount of hydrogen ions that you have in your soil. And this is going to affect a few different things as it applies to the health of your soil. First, a lower pH, which means more acidic, is going to increase the amount of heavy metals that exist within your soil. Heavy metals can damage root systems by messing with the cation exchange, which we'll talk about in the next slide. But overall, more acidic soils typically leads to less plant growth. There are some exceptions to that depending on the species of the plant. So as I said before, pH can mess with something called the cation exchange, and that's what we're going to talk about here. So a lot of nutrients that plants need are heavy in positively charged types of elements. So we have this K here, potassium, which is necessary for plants, and we can see it's positively charged. Calcium, positively charged. Magnesium, positively charged. These are all elements that plants require, and they're all positively charged. The reason this matters is because clay is typically negatively charged because it's typically high in aluminum. So we have this clay here that is negatively charged, and it attracts all of these positively charged nutrients. And this is going to be really important for plant roots because plant roots can then extract these positive ions from the clay, increasing the amount of nutrients they have. So typically, it's better to have higher clay in your soil for fertility because the clay helps hold on to some of those nutrients. Now, hydrogen ions that we talked about in the pH here can mess with this. Hydrogen ions are positively charged as well, so they can kind of take up all the spot here on the clay and reduce the amount of useful nutrients that exist there. So that's something we have to keep in mind when we talk about pH because it can damage soils in that way as well. So how do we test chemical properties in soil? Again, you'll be doing this next week, but we have these systems here, these little jars. You can see we have potassium, nitrogen, phosphorus, and then the pH test. And essentially all we do is we take a sample of water with the soil suspended in it that we want to test, and we put it into each of the containers. And then we're going to break open these pills, drop the white powder inside, and then we shake it up. And these pills are full of chemicals called indicators. And essentially what that means is that they will change color if a certain chemical is present. So for example, the potassium here, if the white powder in the pill detects potassium in the soil, it will change orange to reflect that there is potassium in the sample. So we can use these to determine how much of each nutrient we have, and we can use this as a pH test as well. Again, all of which we will do next week. The last one we need to talk about is biological factors, and we'll talk about this more when we get to the lab next week. But biological factors have a lot of different things that they do in order to impact the health of soil. This includes having decomposers, nitrogen fixers, like we talked about in Unit 1, increasing symbiotic relationships, burrowing organisms, and root systems, etc. So the amount of biological factors you have is important as well. And we saw that on the worksheet that I had you guys do over the weekend with the nitrogen cycle and bacteria. So all of this together, and if we go back to the top here, we can see is all going to determine, fertility. And fertility is a measurement of the ability of soil to grow plants and sustain growth. So all of these physical properties and chemical properties are going to work together to kind of determine that. And that's going to be what's most important for agricultural purposes. For physical properties, typically we prefer loam soils because you get a little bit of everything. You have sands that can help with drainage, but you have clays that can help hold some water in during times of droughts. For chemical properties, we typically like soils that are heavy in clay to help with that cation exchange. And we like soils that are high in nitrogen and phosphorus because those are typically limiting factors. Also, we prefer soils that are typically neutral in pH, or around a 7, because that's what most plants require. Some plants require lower or higher pH, but that's due to evolving to the local conditions. A majority of plants is going to be pretty much in the range between 6 and 8. They're not really going to go outside that. Okay, and that brings us to our FRQ assignment. So for the FRQ assignment this week, you will need to do some pre-lab questions. If you look on Google Classroom, I have 2 labs here. Your job will be to read the overview purpose and the pre-lab activities, and then answer all of the pre-lab questions. Once you get to the lab investigation, that's where you stop, because that's all stuff we're going to do in class. Okay? So again, you're going to complete everything up to lab investigation for both of the labs that are here. You need to get those done before the end of the weekend, so that way we can just get right into the labs next week. So that's going to be it for today, and I will see you all on Monday.